Tak. No, takže ten kurz se skládá kromě přednášky taky z cvičení, které jsou každý lichý týden nebo sudej týden, ale jsou to cvičení formou konzultací k projektu. A ten projekt bude koncipovaný jako takový menší softwarový dílo, který každý z vás udělá v nějakém tématu toho kurzu. Takže celý ten kurz půjde do šířky přes všechny ty témata a vy si vyberete nějaký z nich a zpracujete jakoby zápočtový projekt. A to bude vlastně, protože jsme virtuální, tak to bude vlastně jediná klasifikace toho celého předmětu. Normálně, když je normální docházka, tak ještě tam máme test, ale ten nedává smysl, když jsme virtuálně. Takže to budou vaše povinnosti. Každý ten sudej nebo lichý týden, já teď nevím, jak to je, prostě to máte v rozvrhu, já to mám taky v rozvrhu, tak bude moct konzultovat ty témata a pak průběh implementace těch projektů a na konci bude nějaká prezentace vaše a tím se to uzavře. Tak, dneska máme první přednášku, která je o webu, nebo taková úvodní přednáška, která jako mapuje ten kontext problému webu, webových vyhledávačů a způsobu vyhledávání na webu. A celý ten kurz teda je koncipovaný takhle, jako průnik tady těch různých disciplín.
I'm sorry to interrupt you. I just like to ask, course is going to be in English or in
okay, we have English. Yeah, I forgot we have one English student. Okay, I will switch to English. No, it's no problem.
Okay, thank you very much.
Okay. I repeat, the objective of the course is to give you overview over the topics of web retrieval, and your duties are to implement a software project that is specified as one topic inside the course that you pick, and you will implement some application in this topic. We can discuss every other week. We have consultation exercise consultation term, and at the end of the semester you will present the project. Okay, so the course is assembled by topics from different areas. We will mostly be discussing topics from information retrieval, then also from database systems and other topics like web search engines, computer vision and machine learning, because we also will discuss multimedia data, and some topics from web design and interfaces, because the retrieval is bound to some interface. So the course is about retrieving information from the web. That's why it's called like that. We are interested in searching, browsing, and querying content on the web. And specifically, the content, the basic or baseline content for us is the web pages, which is enhanced text document for us, where there is not only text, but it's hypertext, so text including the links to other sources. So for us, the web graph is the entity that we search in, and we could extend this to social networks that are application specific, but also work on the basis of graph. We also will consider at the end of the course multimedia documents, and there we focus more on the content-based search techniques, because multimedia data are loosely structured or unstructured data that need to be searched on a different way than the hypertext data. So this is what is the course about. Is about the retrieval. It's not about the software engineering point of view issues like web application architectures, web application design, programming, and so on. And it's not about general GUI. It's about interfaces that are only related to retrieval. And also, it's not about the low-level features like or low-level properties like networking, the network protocols, communication level layers, and so on, and the low-level infrastructure. Okay, so today we are starting from the top perspective. We are mapping the problem, mapping the space where we will be moving and discussing. What is the web space? Then we will summarize the basic modules of web search engines, which is crawling, indexing, and searching. Also, we'll talk something about web multimedia retrieval, and then we will more discuss the retrieval modes that are for us simplified to categories of browsing, querying, and filtering. We also will discuss some architectures for retrieval, for multimedia retrieval, which are here categorized to the specific architectures of search engine, hosting servers, and also enterprise applications. So a little bit of history. We are talking about web space, and this is, of course, related to the foundation of World Wide Web, and then standard of World Wide Web that was founded in 1989 by Tim Berners-Lee in CERN. And at the time, this was activity motivated by basically intranet presentation of information, where the creation of the content is distributed, and the representation of the data is directly formatted to display, to presentation. So right from the beginning, the www standard was designed for presentation of graph data. Okay, so this is the basics. We have the graph structure. The nodes are the web pages. The edges are the links between the web pages. And because this must be realized over the computer network, there was also HTTP protocol defined, hypertext transfer protocol, on which the communication is realized. But the most value that introduced the web was that it interpreted the internet as a GUI based space. So the HTML code, the web pages were formatted and written in a way that a person can easily read the content. For the same reason, it is not a format that was readable by machine. So it's not machine readable format. Of course, it is machine readable for presentation or rendering of web page. Every internet browser can, of course, display HTML code, but it's not designed for understanding by machine. That's something that is later more detailed and developed in the semantic web, which we will also talk about, but not at this moment. The basic data entity we will talk about is web page. So web page is a hypertext document written in HTML, which is acronym for hypertext markup language, and there are many descendants and many versions of HTML itself. And at the beginning of web, the web page was considered as a document. So we have many types of documents or text documents, and web page was considered as a digital version of online version of offline text documents. Of course, because of this online nature, it lives in internet, and because it's online, we can also suppose that there are other web pages, and therefore we can refer to these other web pages inside the HTML code in every web page. That's why we have the hypertext markup there, and the linking between the web pages is realized using URL, which is Uniform resource locator, which is basically the biggest invention of HTML, is used till today, and it's the cornerstone of communication on the web. At the beginning, the web page was basically supposed to include full text and augmented with the links. Today we have embedded many kinds of other data types, and it's more like application platform today than a digital library. In the 90s, early 90s, the web was considered as an online digital library, where the web pages were the documents, and we could consider them as a collection of text, huge collection of text. Nowadays, it all changes. After 30 years, we have still web pages, but they are more like containers of web applications. It's not about web pages as documents, but as applications. But still, we will use this baseline interpretation through the course, and also this is supported by the search engine that also index the web as a collection of text, hypertexts. So this is the basic entity web page. We of course can identify websites which are collections of web pages that are related to a certain unique semantic entity, like personal web, newspapers, social networks, and so on. And these pages within this website share some prefix in the URL. From the history, after it was invented in 1989, this could be called something like Web 1.0, which was not named at that day, of course, because nobody knew that there will be some Web 2. But today we can call it like that, and it was the first 15 years of web, and the nature was, as I said, the digital library, online digital library. So there were many web pages containing personal websites, also online news and other types of documents, and was rather a static content where the users were passively browsing this content rather than involving in the creation of the content. This is activity that happens after 2004, where the Web 2 begins, and this is a consequence of many factors that allowed to incorporate ordinary end users to the creation of web content. There were at the time most of the people had access to high-speed internet, which was a very crucial condition to realize more intense participation in web creation. Also, at the time, the web switched to the from the digital collection point of view to the application platform. So there, at the time, many social networks started their businesses, and e-commerce activity started to be more important, and so on. So this all brought the usage of internet not only for passive browsing of content, like reading the digital library, which was the first intent, but taking it as an application and as an interactive platform. So the interactivity heavily changed the internet, because not only a few designated creators made the content, but everybody. I have here some graphs on the client platforms that are used for using of social media applications, and these are quite old numbers, but show us the trend. At the beginning, or the whole 90s and the first decade of of the new millennium, the most prominent platform for using the web was the desktop computer or notebook. But in the last 10 years, we see very huge decline from desktop platforms to mobile platforms. So we can see that not only social media, but generally web applications and web content is supposed to be presented and processed or viewed on mobile devices. We can see that 70% of content was on YouTube was viewed on mobiles. This is 4 years old information, so today is probably more, and even more in case of social networks. Here we can also see the course of the day, where each platform takes place. So we can see that in the morning, everybody is on phone. Then maybe there people are in work, so it switches to desktop usage. And in the evening, again, it returns to the usage of the mobile devices. Again, this is 4 years old, so probably even more today in favor of mobile devices. When we look on the web as a data platform, we can view the web space as a very huge database. And if we talk about data or database, we can distinguish, or we should distinguish types of data that appear throughout the history of databases that could eventually appear on the web today. So through the history, we can divide the data between structured data and unstructured data, starting with relational databases in the 70s, and in the structured part of the of this scheme, where the relational databases, everybody knows them. We have the basic core on databases. This is the easiest or the most machine readable type of data, where it's clear semantic and structure. That's why structured data are often provided with schema that precisely defines the semantics and the structure. In relational databases, we have the tables, the attributes, and the attributes are typed. And therefore, we can use structured query language like SQL that basically allows the end user to specify exactly, using the term of the relational model, what queries the user wants. So the formulation of the query is very easy in SQL, because the attribute number, attribute names, types, and the semantics are transferred to the end user, and they are easily understandable. Later then came object relational model that is basically the same but extended to classes and objects. Then we had the era of XML, where the data were not necessarily of relational nature, but were graph-based, but more tree-based, but generally graph-based. We had XPath and XQuery. Then even later, the RDF standard came that allowed to describe objects of the real world using triplets and queried by SPARQL query language. And then the era of NoSQL databases came, connected with the big data and social media, where we have the key value storages and other standards that allow to process very big data. Nowadays, we have the era of NewSQL, where we try to put together the good properties of relational databases, which is the ACID properties, so the consistency and so on, and the scalability of NoSQL, because NoSQL traded the ACID properties for scalability, and in NewSQL there are approaches to combine these two together. So this is the side of structured data. Of course, mostly this data is on internet. Depends in which form, and it's provided through some API and or behind some interfaces. On the other hand, we have unstructured data that are more specific or they are more typical for web, and that starts in the history with text, full texts, maybe in 70s or 60s, where there were attempts to create digital libraries. The digital library is a term that originated in USA in 70 years old, where there were attempts to ease the searching in written texts, right? But in a normal library 60 years ago, you have to go to the library and ask librarian and maybe use some very primitive registers that were not based on full text search, but basically they were factographic systems. They were registered based on author name and maybe title, maybe ISBN number, and these kind of basically structured relational data. But you cannot search using the full text that appears actually in the text in the book. So at that time, the information retrieval basically started, that was addressing the problem of searching in a huge collection of text documents a content that was specified by keywords or by other text. So this is the first occurrence of unstructured data in large scale or larger scale, and then it followed by other data types that are also unstructured. In this column we have unstructured data, and the unstructured property means that we have no schema, and the data type does not provide any semantical structure that could be used to basically transfer this structure to the user for querying. So there is nothing like the situation in relational database. In relational databases, we had the attributes, and the attribute is a construct that is directly used in SQL. So users can directly use these attributes for construction of queries. We have nothing like that in text. All we have in text is the keyword. And this is, of course, very low level information. And as such, the text is just a plain sequence of words. So it's unstructured, or it's only loosely structured, very loosely. The same situation applies for strings, because we have strings, of course, strings of characters, normal words, but we have also strings of other characters, like we have artificial representations of for example, molecules in bioinformatics. For this reason, the strings are used heavily. And even more general, we have time series data type, where we have again a sequence of values. This is also unstructured. This is only a sequence of values that must be interpreted, somehow segmented, and so on. And the last and the biggest area is sensory data, where also multimedia belongs to, where we have a huge and ever increasing domain of data types that are also unstructured, because they come from sensors, and the sensors are low level. For example, if we have photographs, the sensor is the CCD chip, and we get values of the pixels. Of course, this is machine readable for reproduction. We can show, we can display it on a screen, or we can print it using printer, and we can compress it and so on. But the representation itself is not readable for understanding. So I cannot just read JPEG file, for example, and recognize the objects, because I have only pixels that I only can display. This is a completely different situation from the SQL or the relational data, where the structure provides me with understanding of the data. This is not directly provided in unstructured data. And that's why in the whole category of unstructured data, there is no standardized query language for retrieval of this data. And most of the approaches must rely on a common principle that could be used for search, but cannot rely on the particular properties because they are not known, that they are subject of the feature extraction procedure. And that's why the query context is limited to very general concept of similarity search. So in similarity search, we basically suppose we have black box representations of the descriptors of all of these data, and we can measure similarity between two entities of this kind of data. The measuring itself, the algorithm for measuring and the representation of the descriptors for measuring the data is then subject of the modeling in the particular domain. So the database context for this is the broad paradigm of similarity search. Okay, so this is a brief history of data, and this data could be found on web. And as you probably note, the web search engine work with the web or web pages as with augmented text. So the search engine parse web pages, index the text or the textual content, and then engines like Google provide keyword search to match the relevant documents with the keywords in the query. So the text is the most prominent, or the full text search is the most prominent web retrieval modality, but there are more of them. If we talk about multimedia, we can see this graph, which is quite recent, where you can observe that the volume of multimedia data provided on web grows exponentially. So this graph is just for YouTube videos, and this is only how many hours of video is uploaded to YouTube every minute. So you can see that 2 years ago it was 500 hours of video per minute uploaded to YouTube, and you can see the history. So there is exponential growth. We can see a similar trend in uploading to social media like Instagram or Facebook. There is expected 2 years ago that there is 100 million of photos uploaded to Instagram every day, and 350 million photos to Facebook every day. And they are already storing these two platforms 50 billion or 250 billion in total. So there are huge numbers on that. At YouTube every day 5 billion video is watched. So these are really big data numbers. The factors are, as I already mentioned, the availability of high-speed internet. We also have computers that are capable of processing of multimedia content. Was also not true every time, because 20 years ago there was even challenge for playing a video because of the hardware limits. We have the cloud infrastructure, so we can upload the captured data, the photographed or records of video to clouds. And last but not least, we have cheap capturing devices. Every digital camera or every mobile is a camera, and we are connected directly to the internet, and we upload to this mentioned platform. So we have the whole pipeline of the necessary parts that basically cause this amazing growth of multimedia on the web. And as I said, in Web 2.0, everybody is information producer, so it's distributed, and the web infrastructure is distributed itself, so it supports this trend. There is also huge movement of human activities to the internet, and this, of course, is very actually this is very critical nowadays, where we have restrictions on the pandemic. So we are very grateful for this development that happened 10 years ago, that basically every business moved to web or to internet, but to web as the human platform for accessing services on internet. So we have entertainment, we have e-banking, e-shops, and so on. Now e-learning like today. Okay, So the web information retrieval solves the information retrieval problem on the web and in a large scale. So there are two factors: the online platform of web and the large scale factor. When we are talking about web, of course, the web platform consists of a web server side, where we have the infrastructure that is capable to serve many users. So we have the web server like Apache, we have the database server, we have other kind of servers that provide services, and we have the client side that basically access the web documents. So we have web applications executed in the web browser, or we have mobile applications that are dedicated. But on the background, they often use web standards. So the web is still the basic infrastructure that powers the online communication of people using whatever kind of platform. Okay, and if we think about activities on web, then we must come with the one shared essential activity that we all use, and that is the retrieval of some information. And this is valid for shopping. If you want to buy something, you must find it. This is valid for other, like entertainment. You must find the movie you want to see. This is valid for e-learning. You search for courses. This is valid for anything. So it's like in databases, parallel situation. In databases, in database systems, you can discuss many different functionalities of database system, but all of these functionalities are only useful when at the end you use searching in database, because otherwise, if you only store data and do nothing with the data, then it's useless. So the searching in the data or processing of the data is basically the target function, what you do. And this is the same with web and with data as such. So the retrieval of the data is the crucial function. So we start with the search engine, because we search for data, we retrieve data. And the search engine is historically the prominent mean of web information retrieval. Of course, it's mostly based on keywords, keyword search or full text search. And they are also used additional information for ranking that are specific to the web environment. You can, of course, search by keywords in offline digital libraries where you only have full text. But if you want to use, for example, PageRank, which heavily improved the searching on web, then you need some additional information that is graph-based, and this is not supposed in the plain text representation. So web search engine that uses this augmented information. We have also meta search engines, which is just a slight mashup on top of search engines that basically allow to aggregate search results from multiple web search engines and present them as a fused result that allows to search more effectively. So there are many of them, and it's also good for business competition. There are some servers that allow to compare products like these two. Now, when we get back to the basics of web search engine, it starts with the domain of information retrieval. So in information retrieval that started in 60s, there was an effort to model and index the full text for search. So it's completely different situation than relational databases. In relational databases, we have already processed data that can be directly searched, because we have nicely shaped tables with the rows and attributes and everything, and we can directly use this for searching. In information retrieval, we suppose harder data type, just a text, collection of just text, and we need to search this collection of text based on content. Because in 60s there was no web, so this is older than the whole web. That's why only the textual information was involved in the design of the algorithms and the models. And there were basically three models established, or three categories of models established. That were the Boolean model, the vector model, and probabilistic model. Today, the vector models are the winning ones, the used ones. The Boolean model, we'll talk about Boolean model next lecture, because it's easy to understand, and it also shows some drawbacks and advantages of treating the text as exact information, which is basically the Boolean model. And then we later will continue with vector model that is more appropriate for the assumption that we work with unstructured data that is not precise, there is no schema, and as such we have no or we should not pretend that we have exact information to search for. So that's why vector models are very successful today. And there are also probabilistic models that treat the problem as a probabilistic problem, but so they are similar to vector models, that they provide some ranking of results to a query, but because the probabilistic models require computing probabilities, and there is much more pre-processing needed, then it's more or less a theoretic category of retrieval models because of computational resources and the whole settings of the problem. In 1998, there also was included link analysis into the classical models of information retrieval. This was powered by the structure of web and also by the problems on the web. We'll talk about that in the lecture about PageRank. What we had prior to search engines. So we had the web full of internal web pages, and imagine you are in 1980 or 1990. There are no search engines. There are only the pages where are accessible by the precise URLs. So if you have no information where a certain web page lies, you have no access to that. This problem is known as the findability problem. There exist data, they are accessible using some way, but they are basically not findable because you have not ways how to reach them. So this is the problem of findability of data on the web directly. So in the pioneering times, the first years of web, there were funny things like web directories that were edited by humans. So there was a, let's say, text file listing all of the URLs to all of the pages, to web pages in the world. Of course, this was not useful once the number of web pages increased above some critical number, let's say 1,000 of web pages, and then it stopped to be editable by humans. So this was not a solution to create a directory of sources. So you cannot find anything that was not listed. So it's not only problem of the quantity, but also the frequency of updates, because not only there are many nodes in the web graph, but the nodes also change permanently. The content is changing. If you have, for example, news servers, there are always new information. So it's changing. Okay, so the solution to this problem, to the findability problem of web, was design and usage of web search engines. So the web application, the basic web application that allowed to search based on a query. Of course, in the first years, there were many of different web search engines, starting with the Archie, which was one of the pioneers, where you were allowed to search using the directory of listing from public FTP servers. So this was one approach to that. There was also a W3 catalog but was based on the catalogs, as I already mentioned. There was World Wide Web Wanderer, which was first basically robot that is used nowadays. So crawler of web content. And then it was followed by the commercial and successful search engine like Alta Vista and Yahoo that were very popular in early 90s, but then all of them were basically outperformed by the Google, and it was this happened in 1998. And the reason for the win of Google was two. The main reason was the introduction of the PageRank algorithm, which gave much better results than the other engines. We'll talk about the reasons later. And it was also successful because very simple GUI, where nowadays it looks like a funny reason, but in 1998 many people didn't have fast access to internet and used dialed modem access to internet. So the simplicity of a web page was really crucial for basically delivering information to the user. And when the search engine itself needs a lot of time to basically download the search page, then it discourages the users to use it. And this was the case of Alta Vista, for example, that had built the business model on ads. So advertisement, of course, is business model of any application that is for free. You can observe it on your mobile phones, of course. But at the time of Alta Vista, this was really making it impossible to use almost, because before you were allowed to a query for a web page, you must wait for downloading many ads with the images, and you had the slow dialed access. So this was really very uncomfortable. But Google came with different business model when you are allowed to quickly enter the query, because you have very simple GUI, only the Google logo as you have today. So it's almost 30 years the same. And the ads appear after the search. So once you already see the result of the search, then there are the ads. And this was much more practical for users than the previous. There are many other major search engines like Bing, Yahoo Search, and so on, but Google is still prominent, except, of course, the countries where it is forbidden. Oh, we all know where. When we look on the web engines from the software point of view, we can identify three modules of web search engine. We need to crawl data from the web, index the data into a form that is useful for searching, and then the actual searching. So there are three modules of every web search engine that are connected like that. So we have the web, which is this is just a cloud, but the web itself is basically a network of web servers that provide content. And to these web servers, the crawl module raises or issues crawling requests that must serve the web servers and pass it back to the module, and the module then creates or passes it to page repository, creating offline snapshot basically of the web. This snapshot is indexed in indexing module, where the indexes are created as data structures, and these indexes then help the query module to answer a particular query of a user. There is optionally another module, that is ranking module, that allows to re-rank or provide some user feedback and present the query result in different forms. So this is the basic scheme of any web search engine. The crawler, the first part of the search engine process, that's a short program that instructs robots or spiders to download the content from the web service, as I realized. So there are many copies of the same program that is scanning the web, walking along the links on the web pages. So it's like spider, and the content must be aggregated into one place to the page repository. Of course, there are many concerns when talking about crawler. There are limited resources, of course, because the website is huge, the bandwidth is limited, and we must not only limit the frequency of access of the robots to a particular page or a particular server, but we also must keep track of repeated visits, because we are not only downloading the content once, but we must download it, or the search engine needs to download it multiple times or repeatedly, because the web changes. It's not one fixed web, but it's dynamic. So there are many policies how to not realize so-called unethical crawling, where the resources are basically blocked by web searchers or web robots, and there are other policies like optimization, access, optimize access, prioritize access, and so on. For this purposes, there is also robot exclusion protocol defined, or other protocols that limit the behavior of web search engines to access content that should not be accessed, for example. There are many information on this on crawling the web. For example, these two books. And if somebody is interested in how to effectively crawl the content from web, there are many tricks and tips. Okay, the second phase is indexing. Once the content is crawled by the crawlers into the offline repository, there must be some index built that allows or accomplishes the search using data stored in the index. There are many types of indexes, because we download many types of content, but the major index, of course, is so-called content index that indexes the full text. So the text downloaded from the pages that is then processed to providing the full text search, the keyword search. Then we have other indexes or other information that is used for search, like the structure index, which is basically the metrics, or the Google metrics, for example. If we talk about Google, that is used for PageRank and allows to rank pages based on other information than just the content. So this is the structure index. And then we have other types of indexes, special purpose indexes. For example, if we will search for multimedia content, we could have multimedia indexes, or for example, indexes for images. For all of these kind of indexes, there are other design factors that come with, or originate from the properties of web, which is the dynamic behavior of the web, where nodes appear and disappear and change their content. So we must keep in mind factors like merging indexes, older with newer. So we can do only some delta transformation of the index, because we don't want to every 10 minutes to download everything. So we need to have some update policy. We must also solve problem with errors, with system failures. So there must be some fault tolerance implemented, like in normal databases, maintenance issues, and so on. From the algorithmical or data engineering point of view, we must also consider the different types of data index structures that could be different kinds of data structures, like inverted file. For full text search, we will talk about inverted file next 2 lectures. But for the other kinds of data, like multimedia data, we could use different kinds of structures, like signature files, suffix trees, and so on. Last but not least, we have also applications that allow us to inspect the past content on the web, because we have the historical versions of the indexes. And one of these projects is called Internet Archive Project, web.archive.org, that allows us to basically search in old versions of web, because of these indexes we already had. And this is quite useful web application, because it allows us to observe the changes on a certain web page. And for example, we can track back some conditions of a business that we would like to know. So if somebody wants to see the evolution of content of a web page for any reason, then the web archive is a good source of information. And the last part of web search engines is the searching, where the indexes that are used for search are the full text indexes plus the structure index. So this is the classical combination: keyword search plus the page rank, so re-ranking based on some reputation. That's the purpose of PageRank. We also could use not so frequent type of query, which is full text query, meaning that we are not querying using a few keywords, but using a whole file, whole text that is large. In case of multimedia, we are using mostly the content-based queries. Query by example, we upload some multimedia and search by means of this example. When talking about multimedia, we can distinguish between 2 ways of indexing multimedia. The easier way is to use annotation. If we have some external description, some high-level description that provides us also high-level semantics, this is basically reusing the full text search. So if we have keywords attached to multimedia or full text, where the multimedia is embedded, so we have a web page where there is multimedia image, and there is a full page of text. This text could be regarded as annotation to the multimedia object. We have URL, where there is also full of keywords. We could have classification and other kinds of information, like GPS, because the photographs could be taken, and some locality that could be attached to the file, and so on. So these are explicit information pieces that were provided with the data type, with the data. Or there could be also contextual information, but this contextual information needs the context, and the context is bounded to some particular applications, which is, for example, the social network. If you have a Facebook and somebody posts a photograph on Facebook, and then people comment on that photograph, this could be regarded as annotation as well to the photograph, but it's contextual. It's not provided by the creator of the photograph, but the user, the context. And this is for free, but it also could be very misleading, because the discussion under some photograph could not be about the photograph itself, but something more or less related. So annotation. So this is the easier way how to search multimedia using the annotation. The hard way is to use the content actually inside the data type. So in case of images, using the pixels in the image to create description and use it for search. So these are very context-free ways. This is context-free way to search, where we only have the multimedia itself. And from the reason, from the nature of this information, the features that we can extract is rather low level. We have just a bunch of pixels, right? And therefore, it also lacks a lot of semantics, because you cannot easily interpret a combination of pixels as an object of a real world. Of course, we have now deep learning, machine learning, which basically changed the landscape here, but it's still much more difficult than using just annotation that we have already the high-level information present and could be queried using normal keyword search. And we can have also multimodal retrieval, where we can combine many types of descriptions to achieve a better effectiveness of the search. Okay, so this is example of a image of multimedia on the web, where we have the page on Flickr. We have this this image, and we have many types of other information. So we have the explicit annotation to this image, which is annotation provided by the author or the content creator, which is in the red boxes. We can see the tags. Somebody really made the work to really tag the image. We have the date, we have the title, we have also the GPS coordinates where it was taken, and we can see that it's in Thailand, right? So that this picture is from Thailand and was taken in 2010. There is also contextual annotation in the blue boxes. This is basically commenting on this picture. There is some specific annotation here that you are allowed to highlight a portion of the object and like something like that. But these contextual annotations are sometimes useful, sometimes not, right? So if somebody says "I love it," okay, it's a comment, but it's not about the content, right? Or if somebody just delimits this region and also says "I like it," it says nothing about the content itself. So maybe the most valuable piece of information for annotation-based search is this text. Now we continue with the modes of retrieval. Normally, when we're speaking about retrieval on the web, we imagine Google and querying, but this is only a part of the retrieval process we could use. So query is the most prominent one, but we could also use browsing, and the browsing is not just clicking on the hypertext and just browsing the graph directly, some web graph, but it could be just a scheme that allows us to iteratively basically query. So browsing could be used or could be viewed as an iterative framework for querying, and we can browse until we are satisfied with the result. And filtering is retrieval, basically passive retrieval. Instead of active querying, we can passively accept content that is recommended to us. So that's why it's also called recommendation, and this is what recommender systems are addressing. So we have some long-term query intent, or we have long-term piece of information of our interest, like query user preferences, user history, and so on. That is an information that could be used for the system to recommend information to us. So we are maybe flooding by, we are flooded by information that we do not want explicitly, but that is somehow relevant to our needs or our preferences. And there are, of course, many combinations that are very effective. For example, querying and browsing. That's a natural combination. We start to query, we get some candidates, and then we browse this candidate set. Or we can realize the opposite way. We start browsing because we don't know what to search for, so we browse just and find some inspiration. And once we find something that might be useful for us, then we create a query for that. And the same with filtering and querying and so on. So the combinations are mostly the most practical modes of retrieval you can encounter. So the first one, querying. Querying is the very basic mode, where we assume very strong assumption, that is that we are able to specify our search intent. So we know what we are searching for. This is very crucial assumption. Technically, the query is some explicit formulation of one-shot search intent. So we know what we are searching for. We can explicitly formulate this intent and execute it. We get result and we are done. So queries are not iterative processes. Query is just one batch of actions. So I get search results and I'm done. The query models, there are different query models. The most used are, of course, the keyword-based query models that use the annotation or the content itself, if it's composed of keywords, of course. Or we can use also the content-based model for multimedia, where we are not querying using keywords, but query by example. So we upload file or sketch and image, for example, and we are searching using this example or query by sketch. And what we get is some query result, and the query result could be structured very simply, like it's just a set of results that is not anyhow structured. So there is binary relevance, which is the case for relational databases. In relational databases, the result of a SQL select statement is just selecting the records that were satisfying the query. But among the particular results, there is no order. So you cannot pick something that is better than something else. Everything is relevant and nothing is more or less relevant. So this is very simple, but it may cause problems. Or we can have multi-value relevance, where we have already ranking of the database object or the objects with respect to the query, starting from the most relevant to the least relevant. This is what you have in Google. When you run a query, you get the first 10 results on the first page, starting from the most relevant to the least, and then you can continue by clicking on the next 10, and you get next page of results and so on, and you can basically fetch all of the objects that were returned. Basically, the whole database is ranked, and you are only observing the prefix of this ranking. And once you get the result of a query, you are either satisfied, or you can provide some relevance feedback, and you can continue. You can make the process iterative and allow the engine to expand the query, re-rank the results, and so on, in order to satisfy the user more. Here we have Google. So if I enter a query, vacations of Hawaii, of course, there are some ads, but after the ads, we have some organic content, organic result, but it's still relevant to the query. So we can have vacations in Hawaii. We have vacations, basically the most similar based on these two keywords, and so on. And we have multiple views on the result. We can see general web pages, or restrict to multimedia results, images, videos, and so on, or products if it's a product. The other way of specifying a query, or the way of specifying query for content-based multimedia retrieval is, for example, query by sketch. If we are able to sketch the intended image, because in this case we are searching for images, then we are provided with some canvas, and we can draw what we want, and this is the result then executed on top of this sketch. Of course, this could mean nothing for this particular example, but this is the way how we can retrieve data based on something completely different than keywords. Otherwise we cannot query this kind of data, because there are no keywords attached to this. So we can use by content. Or if we have a good example, so we can upload the example from web or from the computer. Instead of sketching, we can have basically good example of the object itself. So this is querying. Browsing is another mode of retrieval with the assumption that is different. In browsing, we are mostly not able to specify our search intent. We must start somewhere in the search space, and we want to iteratively navigate through the database or through the web, depends what we are searching, in a way that we approach closer and closer to the result. All of these browsing models use some kind of graph abstraction. In the more straightforward way, this graph is explicit, where we really have a graph and walk along the links on this graph. Or, and this is more versatile and more general, we use some kind of virtual or abstract graph where the nodes and the links are not known in advance, but are created during the course of the browsing. So the user basically decides what is the important property of the retrieval, and based on the information of the user in the browsing time, the graph is basically generated and browsed. And because we are browsing graph, it's more rich information than just a collection of entities, for example, text. So also the result of browsing could be presented on a more sophisticated way than just presenting a subset of a collection of something, because we have the graph structure there. So we can not only present the subset of database object that we return from the database, but also a set of clusters, for example, because we have the graph structure, and we can collapse some nodes and provide the user with some aggregated information, like the set of clusters, or some other structured view on the result, like a hierarchy, and so on. When we are talking about browsing a graph, this is something very straightforward in case of web. For example, if you are on Wikipedia page and there are many highlighted links to other pages that are also Wikipedia, that the browsing is really straightforward. You just click all those links, and you're just switching, and you are walking the subgraph of Wikipedia. There's nothing much to discuss here. Much more interesting is browsing the virtual graph. In virtual graph, you basically you are searching the space, the entities in the space, which could be web pages, but there could be also multimedia objects, whatever kind of entities. And you are starting somewhere in some page 0, which is the start of the browsing. And then you iteratively proceed to the result in a direction that is more prospective from your point of view. So, for example, if you are starting from here, which is some random object displayed in the start of browsing. You can issue a series of queries, like we'll talk about KNN queries, searching for nearest neighbors. So in the space, in the data space, the three nearest neighbors are these three. So these three are the candidates for next step in the iteration, and the user can pick one out of the three objects here, and for example choose this one and move in the space from this point to this point and repeat the whole again. So again, from these three nearest neighbors, retrieve the one that is this most prospective from the point of the user, for example this one, and repeat this and again and browse. And finally, the user along this way ended up in this part of the web space or the space, data space. And the graph there was created online. So these were, of course, this could be viewed as a complete graph, but it doesn't make sense if there is edge between all of the nodes. But if the creation of the graph is driven by the user, because the user said, okay, there will be no edge here, but there will be edge here, then the graph is basically filtered during the iterative processing of the user. And we ended in this particular node of the graph. We can see this general scheme in a real case. So let's have this page. This is a page from the Microsoft Photobank Dreamtime.com, where we have a picture of dog, and we have here also summarized or list of other photographs, and we have here basically both representatives, the explicit graph possibilities of browsing and implicit graph possibilities of browsing. In the explicit graph, which means we already have a real structure of a graph that exists, these nodes in the explicit graph are these images, these pictures. These pictures are photographs from the same user as was the photograph of this dog. And therefore, when clicking on one of these pictures, we basically walk on an edge that already existed, because from every photograph there is a link to the creator of the photograph, which is the one that uploaded it. So we can click on any of the thumbnail. We get the thumbnail here to the main view, and basically then this is the same, always the same, because this doesn't change because the user is still the same. Only the view of the actual node changes. So we have these 10 pictures, and we only click between them. But if we want to search more implicitly, we want to browse beyond the portfolio of the user, we can issue a query based on this photograph. And because the photograph is called Yellow Labrador Dog 2, this is the title of the photograph, then this keyword query could be used as a this could be used as a keyword query and return this part or this part of the database of the images, and the user can pick one of them to basically appear on the main page, which is exactly the same what happens here. So we start with the image of a dog, then we query for a similar dog using the title Yellow Labrador Dog 2. We get 10, but here 3 of the dogs. You can click somewhere, and that's how you browsing. So this is the same, but in real settings. You see the node, and you can click on one of the 10 nearest neighbors and get to the other iteration, because this regenerates again, because the new dog, for example, this one is no Yellow Labrador dog, but it's something different. So the query will be different, and also this result will be different. So you will be clicking on different changing changing results. So you will moving in the space and not getting the same results. Okay, so this was browsing, and the last is filtering. And the filtering is basically querying, or it could be viewed as a querying from the other way. So instead of one-shot query request, we can have permanent query request that is formulated as a fixed search intent, of course explicitly. For example, as a query. It could be also interpreted as a database view. You know what is database view. You create database object that is called a database view. You create it using the SQL select statement, and this lives and updates. So database view is updated by data that are changing in the database and is reflected in the database view. So this is similar to filtering. If the whole data space is changing, then the filtering causes that new data is arriving to you as to the user, and that's the reason of filtering. And this is explicit filtering. Of course, the majority of filtering or recommendation is implicit, and this is based on the user preferences, as I said, or the search history of a user, where the user doesn't have intention to retrieve some information explicitly, but because of the behavior and the contextual information, because this is always happening inside some application, the recommendation or filtered results will come to the user based on these implicit information that is gathered in the application. So if you are using, for example, some eShop, and the eShop starts to recommend something, it's probably because you entered some preferences by means of previous clicking on products in this eShop, and now it recommends something. So it's always within some application scope. It's not out of the blue. It's connected to the application, which is the difference, because if you are browsing, you don't need to have any history of you as a user, and if you are querying as well. So querying and browsing is not related to the person to the user that realizes the search, but in case of recommending, it's a crucial part of the recommending process, the gathering of user preferences and history. Example of explicit filtering, we have a very old technology that is called RSS, where we can define mainly this is in newspapers, but it could be also in this microstock hosting servers. You can define a so-called RSS channel, which is defined using a search intent, like here. I can search for dog Labrador, but instead of one term, one short query, I can create a RSS channel. So I will be continuously informed about every new entity that is fulfilling this search query using some RSS reader. So you can use RSS reader using this using the internet browser. You can add more of these RSS channels, and you can have your own feed of news in your RSS reader. This is some kind of old predecessor of social networks, where you can also subscribe to or like or follow of different entities, and then you have your own feed of news. So basically this was the same, but 20 years ago, when there were no applications like social media. Nowadays we do explicit filtering just by liking or subscribing to a group, like on YouTube. There is some group, Planes Cockpits. I can subscribe, and then all new content is recommended to me. So this is the same as in social media. Implicit filtering, this is something different. It's connected to the application that where we search or that we use, and it's mostly automatic process that is based on users' previous searches. So if you are browsing for dresses or other products, then next time you visit the web or the application, it will recommend content that is based on basically queries or keywords that were extracted from the previous results of the searches. Here we can view even more sophisticated scheme of used for implicit user feedback. This is a web page of a travel agency, and there are some trips listed, depicted as 01 to 07, and the user feedback engine that basically captures the behavior of the user on the page can recognize whether the user is observing particular trip, or the user cannot see the trip because it's rolled down, so it's in invisible area. And the system also can record if the user is somehow interested in the trip or in the object by hovering, for example, the mouse on top of the trip, or clicking on the detail, and so on. So these are all implicit informations that could be gathered by the recommender system that is used as a sub-engine here, and then could be used for recommending of content that is personalized. So it's personalized search. The combinations, as I said, they are very, very frequent and most effective. So if I, for example, on Amazon search for a book that is called information, or that is related to information retrieval, I get a bunch of books, and I have another factor for re-ranking, because these are all relevant to information retrieval. So I need some more refined factor that will rank for me the results. And these could be, for example, recommendations of the users. So these are explicit recommendations by stars, but it could be also some implicit information that will re-rank the result. For example, how many books were sold that were relevant to information retrieval. So the re-ranking could be based on different information, of course. In the domain of multimedia, here we have another example for combination of querying and searching. There is a task called known item search in video collections. You have a video collection of many hours of videos, and you are searching in the video a scene or action that you barely remember. You saw somewhere in these videos, but you don't remember exactly. So you need to search this video collection by, you cannot query exactly, but you need to employ interactive search. So you browse and query and combine these together. And then, so you query by something like that. You have some query interface on keywords, on I don't know, color layout, in action activity, and so on. And you see some keyframes from the video, and you can browse through the keyframes. Right, so you can then click on the video, and then you can realize, oh, but in the video I remember there was something different, so I can create another query, and you can use this combination, browsing and querying, in a loop, and finally basically obtain the desired video that you were searching for. Okay, so this was enough for today, and the next time we start with the retrieval models, and the first model we will talk about will be the Boolean models of search, and we'll also have the consultation to the projects. So are there any queries? Are there any questions? for me now. I'm looking. No, the first consultations we have next week. So next week we will consult the projects, but you can already watch maybe the slides that are uploaded to SIS, the PDFs, and just look on the topics that are in ahead that will be lectured, and you can pick one of the topic that you are interested in, and we can invent or develop a assignment for a project, and next time we can discuss that.
Can we pick our own project, or do we have to like choose from the
it's always better that you can pick your own. If you already have some project from another course, or maybe it could be a part of a bachelor thesis or something, it's always better to have this project incorporated in some larger project. So for me it's better. Okay. The more realistic project that will contribute to something else it is, the better. Okay. Right. So
okay.
But thank you. In detail, we can consult this next time.
Okay.
So if it's all, we can continue next week. So thank you for your attention, and goodbye.